Hey, 12th graders. So we're continuing with our 12.2 notes. And we talked yesterday just pretty much about like what is a derivative, where it's pretty much what we've been talking about the whole time. And then we talked about the derivative and using that derivative function in a example problem. And so what we're going to do now is we're going to do a few more examples and just kind of get a little bit more familiar with just using the derivative function. Our next lesson is going to be how do we find the derivative function and how do we calculate that. And that's actually the easiest part. The hardest part about the derivative function is understanding exactly what it is and how it relates back, especially because all of this is all brand new ideas that you've never really delved into before, which is rare in math classes. And so just keep that in mind, that we're just kind of getting a general idea of what these derivative functions do, how they're compared, and you're in a good spot. Okay, so we have a derivative function. This is a function that tells us what the derivative is of some unknown function that we don't know. It says identify the intervals where the function of f is increasing. So the original, right? This is the derivative. And they're saying, okay, we'll use this derivative to talk about what's going on with the original function and where is it increasing or where is it decreasing. So you don't have the original function, but you do have the derivative and you can use that to your advantage. If we graph the derivative function on our calculator, let me turn up my brightness and also make sure that you can see what I'm talking about. We have x squared minus x minus 12. Graph it. It's going to look weird because my window's weird, so I'm going to go back to standard. And it looks like this. Maybe I'll zoom out so I can see what's going on just a little bit more, and that seems perfect. I'm going to quickly sketch the idea of this graph, so then that way we don't have to deal with the calculator for a bit. The idea of this graph is it looks something like this. And what's going on here with your derivative function, so this is f prime of x, so your derivative of x, we know that our derivative tells us what the slope is at any given point. And so this function could be something completely else, but we want to know when is the function increasing or when is the function decreasing. And as we talked about we didn't, so let's add to these notes. One, we talked about your derivative function telling us that there's a positive slope. In other words, it's increasing. Your f prime of x has to be greater than 0. So your original function is increasing when your derivative is greater than 0. Your original function is decreasing when the derivative is less than 0. So the derivative function, when the derivative function is less than 0, that's when your original function has a negative slope. Your original function has a slope of 0, in other words, a change of behavior, a relative maximum or relative minimum, when the derivative function is equal to 0. So keeping that in mind, when we look at this derivative function, if we want to know where this function is increasing, where the original function is increasing, we're actually looking at where is the derivative function greater than 0. So above the x-axis is when your original function has a positive slope. When we're below the x-axis, with the derivative function, your original function has a negative slope. When we are on the x-axis is when we have a constant slope. So that's how we read these derivative functions, is that we're actually looking at, is it above the x-axis or is it below the x-axis or is it exactly on the x-axis? So what we need to know is we need to know where it crosses the x-axis in order to say, oh, well, this function is above the x-axis within this interval as well as within this interval. And then the derivative function is below the x-axis between these two intervals. So we could factor this. If we remember factoring, we're looking for two numbers that multiply to negative 12 and subtract, because this guy's negative, subtract to negative 1. It ends up being x minus 4 and x plus 3, which means that your x-intercepts are at positive 4, 0 and negative 3, 0. If we remember that. If we don't, also your graphing calculator can find it for you. If you go to menu, for TI Nspires, for TI 84s, you go to second trace and then you'll find the 0 there. So instead for TI Nspires, menu, analyze graph, 0, TI 84s, second trace, and you hit 0. Once you get there, for lower bound, you need to go to the left of the first one and press enter, to the right of the first one and press enter. Do not include both of them because then it only gives you 1. Same with TI 84s. You need to scroll to the left and press enter, and then scroll to when you're to the right of it and press enter, and it'll tell you what it is. And then I have to do it, we all have to do it again for your second one. So it tells you that that is your x-intercept as well. So calculator or algebraically, it's all there. Negative 3, 0, 4, 0. So your original function is increasing when your derivative function is above the x-axis, when it's positive. That's it. So we are above the x-axis on two intervals with this derivative function. Here, we're above the x-axis, and then here, we're above the x-axis. So we need to talk about both of those intervals. Remember with interval notation, we talk about x values. So between negative infinity, right, as long as we're going all the way this way, to negative 3, and we have soft brackets. It looks like a point, right? But it's not. It's an interval between negative infinity and 3. We learned this all the way last year when we were talking about functions. And then the union, right? Now that we've talked about probability and statistics, we know a little bit more about what that means. But the union just means, yes, all of this together. So between the interval negative infinity and negative 3. And then from positive 4 to positive infinity is our other interval where the derivative function is above the x-axis. You could write it like that, or you could say x is less than negative 3 and x is greater than 4. For decreasing, I would like for you to try this on your own. We only have one interval, so just try and fill in the blanks the best that you can. Where is this function decreasing? This function is decreasing between here and here. The original function is decreasing when your derivative function is below the x-axis. So you could write it like this, negative 3, 4, or you could say negative 3 less than x, which is less than 4. Either of those are okay. Interval notation, inequality notation. Okay. So that's how we use the derivative function. We don't even need to have the original function, and the derivative function tells us a lot, right? So if I wanted to think about what's going on with this graph, I could draw, and oftentimes we do, draw what I think is going on within those intervals. So if I've got negative 3 right here and positive 4 right here, I know from negative infinity to negative 3, I have a positive slope. So I could draw anything that has a positive slope. And then I know I have a 0 slope here, which means I've actually got like a change in behavior. And then I've got a negative slope. So it could look something like this. And it could still be negative as it reaches to negative or to positive 4. At positive 4, it has a slope of 0. In other words, a changing point. And then it has a positive slope after that, right? So it could look something like this compared to what's going on with the derivative. This could be one example of what your original function looks like. Okay, example 3. The rate of change in a population is given by the function this. Remember, like derivative of y in regards to x, or in this case, derivative of p in regards to t. And we have this function that is the derivative function. It says p is the population and t is the time in years. Hey, t has to be greater than or equal to 0. So it says find the initial rate of change in the population.